Good morning, everyone, and welcome to today's DigiBUILD webinar on digital twins, enhancing district heating with data-driven approaches. We're thrilled to have you join us as we explore how digital twin technology is revolutionizing the energy management and district heating systems through high-quality data and advanced analytics. My name is John Kapetanakis. I'm Senior Project Officer at Rio Power, and I'll be your host for today's session. We have a lineup of experts, our partners, who will share their insights and their achievements within their technical work packages in the DigiBUILD project. Before I start with the agenda, I would like to share some guidelines regarding the Zoom platform and the session. The webinar is being recorded, and the recording will be shared through the YouTube channel of Rio Power and the social media of the DigiBUILD project. We encourage you to ask questions by submitting them through the Q&A function that you can see on the ribbon on the bottom of the screen. Feel free to contact us afterwards, as we will able to share also the slides of the presentations to all attendees. So, for today's agenda, we'll start with an introduction to DigiBUILD and the digital services presented by Stathis Stamatopoulos, Research Associate at the Energy Policy Unit of the National Technical University of Athens. Then we'll move to the presentation by Pablo Marcos, a research engineer at Veolia Servicios Lecam, where he will tell us more about the Spanish pilots run by Veolia and how they work on improving data quality and analytics in district heating. Next presentation is from Jose Hernandez Garcia, researcher at the Energy Division of CARTIF, where he will explain more about the district heating case of FASA, one of the two pilots, and how combining simulation and forecasting affects operation. And the last presentation is by Leandro Lombardo, technical manager engineering, who will present the district heating case of Rio Vena, and will say more about the energy management enhancing by optimizing thermal power. After the presentations, we will be able to address your questions and also have the panel available for discussion, all the speakers. The discussion will be moderated by Diego Arnone, project manager at engineering, and the DigiBUILD coordinator. So let's get started with our first speaker. Stathis will give the first presentation. We will not have time to address questions in between presentations. We will address them all at the end. Stathis, the floor is yours.
Good morning, everyone. I'm Stathis Stamatopoulos, researcher in the National Technical University of Athens, and it is a real pleasure to be here today to introduce DigiBUILD project and its services. As we know, DigiBUILD is an EU-funded project that aims to leverage data-driven approaches to help stakeholders make informed decisions and improve energy efficiency in buildings, and as we will discuss today, in district heating networks. The DigiBUILD approach is built around 4 key objectives: enhancing energy efficiency through real-time monitoring and predictive analytics to optimize energy use, to support data-driven decision-making by integrating high-quality, real-time and contextual data from various data sources, ensuring interoperability integration of data by connecting energy systems and infrastructure with other policy domains, and empowering stakeholders from building owners to policymakers, infrastructures, providing actionable insights for better energy management. As we move forward, we can see here the three main technological pillars of DigiBUILD: the data quality and federated storage, the data-driven and AI-based services, and digital twins. Data quality and federated storage aims at ensuring the reliability, standardization, and accessibility of contextual and dynamic building data, while the AI-based services, with their data-driven nature, leverage analytics to extract meaningful insights for energy optimization. Digital twins, on the other side, aim at creating a virtual model of buildings and, as we will see today, district heating networks to simulate or improve their performance. Moving forward, we will get more in deep in DigiBUILD services. First, we have a cluster of services that are related with energy profiling and forecasting, aiming at improving how we predict and manage energy demand and production. Then we have the data-driven services for energy resource management that ensure the optimized energy use in buildings. Another key batch of services are the data-driven energy and non-energy service for enhanced energy comfort and well-being, monitoring the interconditions and providing recommendations for healthier living spaces. Then we have the data-driven services for innovation roadmaps and energy efficiency financing, supporting decision makers with the best strategies for retrofitting buildings. Finally, we have services supporting decision making under uncertainty for efficient and climate resilient buildings, in which we attempt to assess climate resilience of buildings and their vulnerability to several climate hazards. As highlighted here, DigiBUILD is working in 9 different pilot cases across 8 European countries. Today, we will present one of the key pilots related to district heating, Pilot 4 in Spain. And I would like to give the floor to Pablo Marcos from Veolia, who will now present the Spanish pilot. Thank you very much.
Thank you, Stathis. Good morning, everyone, and thank you for joining this webinar. The purpose of my presentation is to introduce you the Spanish pilots in DigiBUILD, improving data quality and analytics in thermal networks. We're going to talk about the details of 2 pilots, FASA in Valladolid and Rio Vena in Burgos, both in Spain, where we will explore how we can improve, as I said, the data quality analytics in thermal networks. Both sites operate a district heating network and have implemented an advanced management system, including building management system, energy management system, and district energy management system. On the one hand, at FASA, the district heating network has 20 distribution substations, 20 buildings that provide heating and domestic hot water to 398 households, fueled by 2 biomass boilers and 1 gas boiler. So in total, we are using 90% biomass and 10% natural gas. And on the other hand, at Rio Vena, the district heating network has 23 distribution substations that provide heating and domestic hot water to 706 households. And in that case, this district heating is fueled by 3 gas boilers with a capacity of 30.5 megawatts using only natural gas. Next slide, please. Okay, so in the next slide, we show more in detail the characteristics of one of the pilots, FASA, which has 3 independent circuits to supply heating and domestic hot water to each of the buildings. And it also shows the schema that the photovoltaic system provides a small contribution to all the residents of the district heating, not only to the users that are living in the FASA tower, which is the bigger building in the right of the picture. Next slide, please. The 3 boilers of the production plant are internally monitored by Veolia, as well as each of the substations, whose component layout is basically the same, which is the picture on the right, excepting that the tower includes the photovoltaic system and the water tank with the 8 electric resistances. Next slide, please. Okay, now with this schema, the substation layout, considering the FASA tower, we can see the supply circuit, which is the red arrow, and the return, which is the blue arrow. This is interesting because it serves as a link between the production plant, from where we come, on the left, and the user's utilization of both heating and domestic hot water, which is on the right. So in this layout, we talk about the primary circuit belonging to the heat network and the secondary circuit belonging to the specific building. Next slide, please. Okay, so regarding the data sharing possibilities, we have historical data available in Veolia's hub rate, which are the smart management centers for our water, energy, and waste business lines, allowing Veolia teams to monitor and optimize management of resources of their clients, and using it through our SQL database. First one at TP FASA since November 2018. We are using 768 variables with a monthly size of more or less 290 megabytes. And here our new feature is this. In this project, we can be able to share CSV files through an SQL download that connect to our Veolia's hub rate, and subsequently we are able to send those files to the STP server that is currently being shared with engineering and CARTIF. Moving on to Rio Vena, the strategy is the same, but we have collected data for 11 variables since week 17 of 2023, because previously we had only 4 variables, which are the cumulative energy and volume and operational hours from boilers 1 and 2. So thanks to this standardization of this process, it allows us to share files monthly, weekly, or even daily without too much effort, although we have to continue working on being able to share data in almost real time. That continues to be our biggest difficulty internally, but in terms of DigiBUILD's project, there are not any difficulties or risks associated to our pilot. Next slide, please. Regarding the demonstration activities, the first services is interoperability in order to improve data quality in the hub rate, Veolia's hub rate, by consolidating data sources in the current energy businesses of thermal networks. And then we are introducing 3 specific services that will increase our project capabilities. First of all, a district network production forecast will play a vital role in adapting energy consumption based on external variables such as weather forecasting and internal variables. I mean historical databases or sensor inputs, and simulations, on the other hand, based on digital twin. A second service is a district network production economic optimization that selects the optimal energy source based on performance and cost. And moreover, in order to ensure data quality and provide useful data, we will develop a district network digital twin, which will act as a dashboard for data quality report. So by approaching the capabilities of digital twin and the rest of the services, we can simulate different energy management strategies, enabling us to evaluate and fine-tune our approaches to further optimize the overall performance of the district network. So, all in all, we can improve our ability to make data-driven decisions and optimize energy management with the district heating network. That's all from my side. In the following slides, my colleague Jose will explain in more detail the services that CARTIF has developed. Thank you very much.
Hello, good morning. Thank you, Pablo, for introducing myself. Good morning, everyone, and thank you for attending this webinar. I'm Jose Hernandez, from a researcher in data-driven approaches in the energy division in CARTIF, and I will continue with the approach that we apply in the Veolia demo site, in this case FASA. But before going to the digital twin, let me connect how the data is being integrated in the data lake within DigiBUILD. So in this sense, as introduced by Pablo, Veolia is providing data in CSV files based on FTP servers. So we can see this is the part of the pilot repository that we have in DigiBUILD. But in DigiBUILD, we count on data lake that is combining data warehouse in form of time series database in order to store all this dynamic data about the operation of the facilities, in this case from Veolia, but also for the rest of the pilots that we have in the project, sorry. And combined with the static data that is providing contextual data and enriching our data lake in order to have contextual information around the time series data, and then providing additional information that is useful to apply the services and in the digital twins. With this, we have a set of data marts that are combining the different information from the data warehouse and the static data to be shared via an interface, an API, based on SQL queries, and then providing the information and the data for the services and digital twins in an harmonized way, and using a DigiBUILD data model in order to have this kind of common data model for all the data sets and setting in a common way for the services and digital twins. And of course, providing some user interfaces for the end user. So this is how the information is being connected from the transition from the Veolia side to the digital twin. So we are using in the middle this data lake, and this is something that I will explain later as well in the schema of the digital twin that we provided in FASA. And in this sense, how this collection of data is being working. Basically, we have an ETL, an extraction, transformation, and loading procedure that is based on a job that automatically collects the data from the low-level interface from the pilot repository that Pablo showed before. And we have a transformation that transforms all this data in a common format, as I mentioned before, in order to be stored in the database. So with this, we assure that all the data from all the pilots is in the common way and can be enriched with the static data that I mentioned before. So basically, just to show you an example about how this transformation is being made. So we have a set of blocks that are doing some functions in different, using the data set that we have. So just transforming the data, I will not enter into the details about how this transformation is working, but just to show you that the way of transforming the data is based on different steps that converts all this information, having not only having the information that we have in the different data set, but also obtaining some metadata that will be used for the static information that I mentioned before. That is very important to enrich the data. So we are able to extract also metadata from the original data set that we have in the pilots whenever this is available. So just to show you the sample of this case. And as I mentioned before, the digital twin of the FASA district is being composed of a couple of data sets. First of all, static data. In this case, static data is the driver that we have for the digital twin. In this case, using a CTGML-based model. So we model the buildings, but also the district heating network, as you can see in the snapshot. So we have the circuits, we have different pipes, we have buildings, the boiler system, and how we connect all the different elements. So this is the way that we enrich our time series database. And on the other hand, complementing the schema that Pablo showed before, we have the dynamic data that is being collected from the system. So we have the combination of both data sets in order to have the complete data for the digital twin. So basically, we are using, of course, the operational data as our data-driven approach, but using also the static information, the different topology of the network that will be our contextual data to enrich this information to have a more accurate digital twin and services applied in the FASA district. So with this, we have this approach. Until now, I have shown these two parts, the district heating information model and the SCADA, that is the operation data. So both is worth to mention that are synced because we have different IDs of the devices that are in the system that are connecting the static and the dynamic worlds in order to assure that the data is unique and coherent and consistent. All this information is being composed in a data mart, as I mentioned before, following the data lake. So basically, these three components are being the main components of the data lake. And thanks to this information that is using the network topology, as I mentioned before, and the real-time operation parameters, we are able to simulate the network. We are able to obtain the different heat and pressure losses that we have in the network, and also predicting these thermal and pressure losses in the system, because sometimes this part is neglected, but we are introducing also these aspects within our digital twin because we should take into consideration this energy into the generation system because we need to cover the demand, but also the losses that we have in the network. And on the other side, we have the demand, the production forecast, that is composed of two different functions. First of all, the demand that we have in the buildings. So predicting the demand that the building will, or the needs of energy that the building will have in order to cover the comfort parameter or the comfort levels that should we assure. But also, as Pablo mentioned before, they have a power to heat system based on a photovoltaic system, and we are also predicting the contribution of this renewable energy. So basically, at the end, in the optimization service, we have the demand profile that we have from the buildings. We have the PV production prediction from the power to heat system, but we have also the prediction of the thermal losses. So having all this information, having all this forecasting of the systems, we are able to optimize based on an algorithm the different use of the boilers. Basically, in this sense, the set point of the boilers and the use of the thermal tank, the inertia thermal tank they have in the system, in order to provide some recommendation to the operator in order to reduce or to optimize the use of these boilers. And first of all, in the sense of reducing cost and in maximizing the renewable energy to be used in the system, but also increasing the life cycle of the boilers by balancing the load of these boilers, and then providing a better informed operation system of district heating. Of course, everything with the participation of the user, because not only providing this recommendation, but also the user will be able to configure the different elements or different scenarios that we want to run. So basically, here, just to wrap up this schema, we are combining both static information, dynamic information, forecasting, and also real-time optimization network. So having this cocktail of different elements, we are able to provide optimized or optimal parameters in order to operate the network from the facility manager perspective. And just to conclude with my presentation, I would like to show you a couple of snapshots about the digital twin of the FASA district heating. So basically, this is the main screen that we have in the system. So we have the buildings that are part of the digital twin. So on the right side, we can see the red building that is selected in this case, with the different information that we have from this building, like the cadastral reference, address, the build area, heated area, the window facade, and the energy demand of this building according to the energy performance certificates. And also, not in this snapshot, but in the new release, we can see also the forecasting of this building. So the facility manager, in this case, as final user, will be able to show also the 24 hours horizon of demand for this building. And in the second screen is about the optimization part. Basically, the user will be able to provide some information about the scenario, like the cost of the energy for biomass and for gas, the set point that they want to apply in the boiler, the set point for comfort and so on, and the system will optimize this energy, but providing the results in different ways. Here in the screen, we can see the simulation results about the different circuits of the system, the heat losses, pressure losses, and the different. This is a simulation that I will not focus on the results, but because maybe the numbers are for synthetic numbers that were generated. But just providing the information to the facility manager, and also here is not shown in the screen, but also the recommended parameters for the operation of the boilers. So basically, all this information is like a bidirectional communication with the user and providing all this data to the user. So with this, I conclude my part, and I would like to pass the floor to Leandro, that will provide the next part about the Rio Vena district. So Leandro, the floor is yours.
Thanks, Josep. Good morning to everyone. This is Leandro Lombardo from Engineering Informatica. Now, today, in this last part of the webinar, I'm going to present the digital twin that will be implemented for the Rio Vena district heating case. This digital twin allows the district heating network manager to boost district heating management, optimizing the heating power. In particular, the Rio Vena digital twin can be considered a support service for the district heating network in order to guarantee operational efficiency and also saving costs, reducing, as a consequence, the CO2 emission. This digital twin allow the manager, that is the end user, to have an overview on the state of the district, and also provide him with strategies aimed at optimizing the consumption of the gas used for heating the district. Next slide, please. Like for the FASA heating case, as it is possible to see from this image, the process for the realization of the digital twin started from the collection of pilot data. I want to point out that the only necessary data are collected to create the virtual replica of the district and also to run services. Like for the FASA digital twin, dynamic data coming from pilot sensor, several pilot sensors are combined with the static district data and are collected after a transformation process, the ETL process, into our data warehouse. From there, a series of datasets that constitute our data mart are then provided via specific APIs to the digital twin and to the service that is made for create optimization strategies, and then are visualized via the final user interface. Next slide, please. So here we can see the schema, the I/O schema for the optimization services. The optimization services is the core component of the Rio Vena digital twin, and this services is meant to work as a backend services, supporting the functionalities of the Rio Vena digital twin. In this sense, let me say, to improve easiness to use and also a good user experience, no user input is required from the digital twin user interface, and all required data are automatically taken from the DigiBUILD data warehouse through an intelligent query system. About the data, we can see on the yellow square that we are taking consideration several historical data like boiler temperature, natural gas historical consumption, working hours, boiler energy, delta T boiler, and so on. These are only an example of the possible data that we are collecting and using in our digital twin. On the right side, we have the core component, our services that is made by two submodules, let me say. The machine learning models that estimate boiler efficiency that is combined with an optimizer function that calculate how to minimize the natural gas consumption. The result is a series of optimized temperature that the manager of the district can apply to the boiler to save cost. Next slide, please. So here we have a few screenshots from the digital twin user interface. On the left side, we can see the dashboard that is an informative dashboard that shows to the manager several parameters within the district via specific graph. The manager can do specific inquiry to the available data. And on the right side, the simulation page. The simulation page is the part of the digital twin where the manager can run the optimization services that in any case is executed every night, and to obtain a series of possible temperature-like strategy to be applied to the boiler of the district. Next slide, please. Last but not least, I want also to point out the attention on the maturity level of this digital twin. We took in consideration as a maturity level the definition of the Institution of Engineering and Technology. We can say that this digital twin achieve a level of 3 in this range, because it cannot directly control the district heating network plant, but provide strategy to be applied to the boiler temperature. And the level 3 is also guaranteed by an automatic data stream, even with daily frequency, to provide data from the real world to the digital representation. So next slide, and now we will have a video with the demo of the digital twin. So please, let's go with the demo.
Here is presented the digital twin implemented in the context of the DigiBUILD project for the Rio Vena district in Burgos, Spain, a Veolia pilot site. The digital twin is designed to provide an optimal management and operation of the district heating. The digital twin accessible via the DigiBUILD toolbox, which contains all the major project results in terms of services and digital twins. On the left side of the toolbox it is possible to find access to all available digital twins created for DigiBUILD project and choose the Rio Vena one. The digital twin authentication page is presented to access the digital twin. The user can then access the service using his own credentials. Access credentials are provided in the context of the DigiBUILD project by admin who manages and controls them, acting on an authentication system based on the key clock. After logging in, the authorized user is redirected to the application composed by two different pages: the dashboard to monitor the status of the district, inquiring, visualizing, and combining historical pilot data coming from different sensors, and the simulation page, core component of the digital twin, where it is possible to run the optimizer engine to obtain strategies on temperature to apply on boilers to optimize the heating power. Starting from the dashboard, the user can choose the period and type of data to be displayed. To choose a time range, the user can select some default time ranges from the time drop-down box that offers different granularities, starting from the previous 6 hours and going back a week, with possibility of setting a customized range with start and end date. For the type of data to show and compare, the user can choose sensor of interest or select multiple ones like distribution return temperature, distribution supply temperature, natural gas consumption, volumetric flow rate, and so on. At the top of the page, relevant metrics calculated from the received data are displayed, such as the total natural gas consumed until the chosen end date, the gas consumption for the selected period, and the average temperatures of boiler 1 and 2. As it is possible to see here, some examples of data visualized and compared about the distribution return temperature and supply temperature for the last 5 days are shown. Here's another example where a custom date range, defined by a specific start and end date, is used to analyze data, such as the volumetric flow rate, over that period. This approach can also be applied to any other sensor of interest. The second page is the simulation page. Here the simulation, automatically scheduled every night, is showed reporting simulation strategy for selected boiler and suggesting time by time temperature to apply to the boiler to optimize the district gas consumption. The manager have also the possibility to launch the simulation engine manually and perform the gas consumption optimization by clicking on the Run Optimization button, running again the optimization engine based on ML models and historical pilot data and optimization function. The optimization strategy, as a result of the performed simulation, is depicted as a time series in which the user sees the temperature that should be applied to the boilers to achieve the gas savings for the given day. The user can select between different boilers to receive optimization results and metrics specific to each one. On the upper side of the page, some widgets display overall optimization metrics, such as the total gas consumption before optimization, the optimized gas consumption, as well as the total gas saved compared to the total gas consumption for the given time period, and the percentage of saved cost if the optimization strategy will be applied. All these metrics allow the district manager to have a clear understanding of the benefits of applying the optimized strategy, which implies also the reduction in CO2 emissions.
So, thanks. And now I want to give the floor to Diego Arnone for the discussion. Thank you.
Thank you very much, Leandro, for the presentation, and thanks to all the speakers for the presentations and the preparation of the video, of course. Now it's time to discuss, so I would encourage the audience to submit their questions through the Q&A box. But first, I would like to ask Diego if he has any comment to start with, or any questions to ask our speakers.
Thank you, John, and thank you to the audience. I see that really many people today joined the webinar, so I'm quite happy that the work that we have done and we are still doing in this project can be disseminated so that we can collect your feedback, your comments, your questions. So I'm quite glad to take part of this initiative. Yeah, basically, this question is for all the speakers and it's related to the adoption of the digital twins. I would like that they explain to the audience which are the main benefits of using for the end user, especially for end user to use the digital twins. So, which are the benefits? Why we should use digital twins? Which are the benefits for the end users? Because digital twins is something that is adopted. Sometimes it's something that we put in many projects because it's a, let's say, technological trend. I don't know how to say, but our project is focused on this topic. So we must explain why, for end users, the usage of a digital twin is important. I don't know who wants to
Maybe
start.
I can start. I can break the ice.
Okay.
So yeah, from my perspective as developer of one of the digital twins for the end user is yeah, as I mentioned before, one of the things is the combination of data that sometimes is not available on the side of the end user, and providing more or better informed decisions, because we have the facility manager, in this case Veolia, has the operational data in real time, but they don't have the capability of having all the information in a historical way and train the models and then have a more accurate result about the optimization of the boiler. So it's something that the combination of the data, the capability of training models, and the use of simulation tools from the FASA case perspective can provide one of the key benefits for the user is taking decisions based on real operation of the system, not just based on the real time, but based on the historical operation of the boilers, the historical operation of the systems, and how the systems or the performance of these systems are affecting the final demand of buildings. So this historical information that sometimes this facility manager don't have the capability to train these models, I think this is one of the key benefits that the end user can have.
Okay, Jose, you are responsible for the data layer, basically. So you are basically interested and you're working on the first foundation, probably, of the entire project, because services are data-driven services. Digital twins need data and need also data-driven services and so on. So it's basically the foundation. Digital twins depend on data. So there's a strict dependency between digital twins and data. So how important are data for them, and what kind of difficulties can come up because of this strict dependency of digital twin from data?
Yeah, you are completely right. So data is the key for our models, for our activities. And as I mentioned before, the combination of data, not only from the operation, from the dynamic world, but also static world, that sometimes is neglected. And one of the key factors of the challenges is the interoperability, because we have data in different formats, in different frequencies. We have gaps of data, and sometimes we are training models as well with data that is not accurate enough. So thanks to the data lake that we have in DigiBuild, we are improving this data quality thanks to different mechanisms that I know that this is out of the scope of this webinar, but it's very important at the same time to improve this data quality. And thanks to this data quality that we're improving, we have more accurate data-driven models. We have more accurate data-driven approaches and services that the end user, and linking to the previous question, the final user can benefit, because we are assuring that our services are high-quality services, then high-quality digital twins, and then taking decisions based on more accurate data and more interoperable data.
Okay, thank you. Thank you, Jose. I think it's quite clear. In the meantime, I saw that there are some questions. I don't know if you, John, want to proceed, but I can take inspiration of these questions. I see Sebastian Grimm ask which operation mode is basis for the calculated savings by using the optimization tool. Is the basis is the basis for the calculated savings by using the optimization tool. So I suppose that this question is for Leandro. So I don't know if it is clear to you.
We can say that the optimization tool, as I presented before, is made by two main components, and the part that is relative to the saving cost is made by a dedicated algorithm that been implemented by our developer that take in consideration historical data coming from the pilot, and with some constraint, and also the estimated boiler efficiency to have as output the possible temperature that must be applied to the boiler to saving cost. It depends on the historical data and how the historical temperature provided benefit for the district heating case. It is an algorithm that is wrapped inside the optimizer, let me say. I don't know if you want to add more. You are muted, Diego.
Oh, sorry. I can jump to the second question of Sebastian Green, even though there are also other questions. And it says basically a short sentence is asking a short sentence about what is a digital twin in your perspective. So basically, which is your definition of digital twin? It seems to be some kind of selected and high quality data extracted from the data lake, but it seems to have a benefit itself as there was no connection from the digital twin to the services, but directly to the end user. I don't know if you can read the okay.
From our point of view, a digital twin is a digital replica of the real world. In our case, when we talk about the real world, we are talking about, as the ISO standard, about our target entity. For the DigiBUILD project, our target entity is the district heating. The virtual replica is made by several elements that are mainly based on data. Static data that represent the district, like the building, static parameter, and the dynamic data that comes from the sensor. In this case, our digital twin, having inside all of this data, can represent a virtual replica of the target entity and allow the manager, the user, the end user to have within one element all the characteristics of our target entity. We are not only talking about, I need to read again the question. We are not only to talk about data set from the data lake.
Yeah, and if I can complement the Leandro answer, also I have to say that it's not only about the user, because in our case, in the FASA digital twin, we have the user interaction bi-directional. So user is introducing data in order to configure different scenarios, also receiving the data. We are connecting the data lake. So, but not only in the way of having historical data, but also we have a real-time connection via Kafka broker that provide us the real status of the network right now. So as Leandro said, is the digital replica in order to know the status in real time. But we have also the services. So in this sense, as I showed you before in the schema, we have the forecasting services that is based on data-driven models based on historical data, but we have also the optimization model. So it's a composition of different elements that are being configured based on two inputs: the data from the dynamic or the real operation of the district heating network, but also the user configuration. So in this sense, we are reconfiguring the different scenarios based on the digital replica of the real status of the digital twin and providing the output to the user.
Okay, thank you, Jose. So let me go to a question that I skipped before. Manuel Pio Silva that asked, is it possible to connect nowadays any of the digital twins presented to other models? For instance, the energy gas distribution digital twin. I'm quite curious about this answer too.
Well, I don't know, Leandro, you want, or myself, I can start. And yeah,
Yes.
at the end, as you showed, we have even in any of the two digital twins that we have, FASA or Rio Vena, is composed of the connection of different elements and different components. So basically, these components, as I mentioned before, are configurable, and of course, they have a high level of replicability. Meanwhile, we are using the same interfaces to connect. I mean, interoperability is one of the key challenges in this aspect when we work with data. So basically, using the same data format in order to share information, the models and the different components can be composed in different ways in order to provide optimized result of the digital twin. Of course, these kind of models that are created are not of general purpose because the configuration of the network are not always exactly the same in all the districts. Is highly replicable and highly usable in different contexts by using this, as I mentioned before, the data formats and the interfaces. And also sometimes some minor adaptation would be required, but of course, using different models are possible. And in this sense, with this exercise that we have made with Veolia case, we have two different approaches for two different networks into different technologies, and we are showing similar results in terms of objectives of cost saving and renewable use. So the answer would be yes at the end, because as demonstrated here, with different approaches, with different models, we are having the similar result. So the adaptation is quite flexible, but again, using or assuring that communication is in a standard way.
Okay, I don't know if someone else want to add something. But I think that Jose explained. Basically, the answer is yes, as possible.
From my point of view, I totally agree with you said.
Okay.
And Diego, what I would like to add to Jose is that following a semantically enriched approach, if only we want to apply this methodology to another model, if only it has the appropriate data and follows that DigiBUILD data model, we can, of course, apply to any other model that we desire.
Okay, thank you, Stathis. And we have also a question from the Desiree response. I don't know if the pronunciation of Sami is correct. Basically, she is asking, does the optimization algorithm only minimize natural gas consumption? I suppose the energy stays for natural gas consumption. Doesn't it try to maximize comfort at the same time? So is the compromise between minimizing the natural gas consumption and maximize the comfort. So basically, she's trying to understand which are the functions, the optimization functions that we are going to manage in terms of minimization and maximization, minimizing natural gas consumption, maximizing comfort. So this is the question.
Let me say this is a direct result. When we talk about optimizing the consumption of the gas, we are not talking about to decrease the comfort at a district level. So this
because
is
it could be very easy to minimize by simply switching off everything. So but I mean, the question is how much we are considering, because of course, if we minimize natural gas consumption, this could affect the condition of comfort. So how much we are taking them into consideration, how much they are considered in terms of optimization, because maybe comfort doesn't need to be maximized, but at least must be kept over a certain limit, over a certain threshold that must be respected. Otherwise, we can simply switch off everything and it's okay.
So maybe colleagues from the pilot.
Pablo?
Pablo is muted.
Pablo, are you muted?
Yeah, sorry, I was muted. I agree with your comments, because it would be very simple if we only try to minimize the energy consumption, but we should also consider to obtain a good comfort. Maybe if it's obvious for me that if you are reducing energy consumption to the minimum, you are reducing comfort. But even if you are, let's say, maximizing energy consumption, you are also maximizing the lack of comfort. So it is a compromise between both of these concepts.
Okay, thank you, Pablo. And okay, there is also a question from an anonymous attendant. And how accurate is the virtual replica? Is it reliable for operational management? So basically asking, if I understand correctly the question, if the work that we have done till now can be used in an operational management in terms of digital twin. So it's something that can be, let's say, sold on the market, or can be used in an operational context, something that is more close to a commercial solution. So before that you provide an answer, I want to specify that we are talking about a research project that, of course, in most of the cases, develops software that can be considered as demonstrators, as prototypes, but it doesn't mean that tomorrow this cannot be considered something that is ready for the market, because one of the activities that we have in the project is the exploitation. Sometimes a sort of re-engineering of the solution could be necessary. It could take a couple of months, depending on the complexity of what has been developed. And of course, it could need some adaptations to be used and exploited in a real environment. But we are talking about a real life pilot. So we are not far from, I mean, maybe I can say a product, but something that can really work in an operational context. But anyway, I want to leave the floor to pilot leaders and to developers just to explain which is the current situation, how far we are from a commercial product or something that can be used in an operational management context.
Yeah, I would say that the digital twin, or the virtual replica, let's say, is enough or more than enough accurate to be applied in the operational real world, the operational management, because the models have been trained to be enough adapted to the real world. So first of all, we train the models with real data, and we compare the expected results with the future model, the future expectations from the results, and we check that this is a real link between the digital twin, the replica, and the real model. So if the expected results from the digital twin implies that we need to edit the temperatures from the boilers, the schedules, or we need to complicate the relation between the external variables and the inputs in the boilers or the circuits in some of the substations. This is something that it can be done, of course.
Okay, thank you, Pablo. As I said before, basically the pilot in the DigiBuild project are real-life pilots, so I'm not a laboratory pilot of something totally simulated. We took inspiration from real data coming from real pilots, so that's the reason why the exploitations in terms of, let's say, something that can be put on the market is easier because we start from a real situation. So thank you, Pablo, for the answer. Okay, we have another question from Sebastian Grimm. She's asking, do you have detailed information or recommendations for ontology and data model standards to us for district heating models, digital twins, or is that something you developed and published during your project work? So this is quite interesting question, because when we talk about district heating, they want to know if we have, referring to ontology or data models that are standards for what concern the district heating, and the digital twins too, or it's something that we developed in our project. So I think that
Diego, first of all, okay, I provided an answer as a link. Yeah, providing the DigiBuild ontology, which is open source. So Sebastian can go there and see details regarding DigiBuild ontology that we use. But to give an answer, although we don't have the leading the partner that leads that led this activity within the project, the definition of DigiBuild ontology, I'm pretty sure, and based on the deliverable 2.3 of DigiBuild, we know that several standards were reviewed in order to define DigiBuild data model and data and ontology, in order, and of course, enriched based on the needs of DigiBuild, in order to have a complete model to serve DigiBuild's purposes. So for sure, the ontology and the data model of DigiBuild is not is something not built from scratch, but expanded based on DigiBuild's needs, but of course based on several standards that are used in industry.
Okay, thank you. Thank you, Stathis. And we have another question from Paul Kuipers, I suppose. They are looking for a system which optimizes the use of renewables in the heat grid, like a wasted heat, in combination with electronics they supply for the heat interface units in the homes. Can your system also do that? So this looks like opportunities to exploit the results of the project. So combining existing systems, they provide electronics, and they are looking for a system that is able to optimize the use of renewables in the heat. So for instance, the use of waste heat. So how can we reply to this question?
Okay, yeah, I will take the floor for the case of what we are doing in the FASA case. So basically, in our approach for the creation of the digital twin is a semi-automatic approach. So it's not completely applicable 100% automatically. But yeah, based on this ontology that we have and the use of the knowledge graphs that we have within the project, we are able to obtain, once we have the configuration of the interfaces for the data, we automatically generate the digital twin or yeah, let's say the simulation network for the system that we have and the creation of the models for the training. So, but this requires an initial configuration because, as we mentioned before, we rely on data, and this data differs from pilot. So sometimes we rely on the names of the data sources that we have, or the sensor IDs, but at least some configuration is needed. But so that's why it's not 100% automatically applicable, but it's semi-automatically, because once we have this interface of data, we are able to automatically generate this knowledge graph that will drive the generation of the simulation network and then the models to optimize the system. But yeah, basically, the way to apply this is to configure the inputs of the digital twin. I hope that I more or less answered the question.
Okay, thank you, Jose. Of course, what comes up from research projects like this is not a product that you can, let's say, install in a number of different situations and just configure and it's working. But it develops skills and software artifacts that can be easily adapted, combined with existing software based on stable methodologies. So we define approaches, models. So I think that it's something that can be adopted by our people. Yeah, I have just another questions because I think that the concept of digital twin could be better specified. I want to give to my colleagues the opportunity to specify better the concept of digital twin, because when we talk about digital twin, we talk also about maturity model, and we know that in different pilots we have different maturity, different level of maturity of the digital twins that have been developed so far. For instance, the digital twins in Rio Vena is at level 3. So my point is, since someone already asked about what is a digital twin from your perspective, I don't think that we have a perspective that belongs only to DigiBUILD. We try to refer to the definition of digital twins as it taken from literature, from scientific literature. So we cited a specific maturity model matrix, but we know that also other maturity models exist. There is a generic definition of digital twin, more than one. But the point is, once that the maturity model is taken as a reference, how can we move from one level to another? What we need to do to improve the level of maturity of a digital twin? In case of Rio Vena, for instance, we have a level 3 digital twin. How can we move to level 4? What kind of effort is required? What kind of functionality we should have? And if this is easily to get?
Hi, Diego. Nice question. You are right. Our digital twin, the Rio Vena 1, currently achieved the level 3. It means that it receives data from the pilot in real time or near real time, like the case of the FASA pilot, and also can provide some strategies, in this case, optimization strategies. We can move to level 4. What does it mean, level 4? Our architecture, the architecture that we have implemented, allow the exchange of data between the real world, so the district that represent our target entity, and the digital twin. Currently, we only collect data, but our architecture is ready to have an exchange of data in a bidirectional manner via the APIs and also via publish-subscribe system. So having this bidirectional interaction, we can reach
I see that Leandro is freezed. Maybe it's only my problem.
No, it's for me too. It's for
Okay,
everyone.
so probably it's his connection.
into the FASA district, into the...
Sorry, Leandro, if I interrupt you, but we lost you for, let's say, 20 seconds, maybe less. So if you can repeat.
I was talking about the fact that it is possible to move to level 4, maturity level 4. We know that our digital twin is currently level 3. It means that we receive data, the digital twin receives data in real time, and also can provide some optimization strategy. The next level is to have a bidirectional exchange of data from the real world to the digital twin, from the digital twin to the real world, that is our target entity, the district heating, and have also the potentiality to send message to potential actuator system deployed in our target entity to trigger the strategies that are provided by the digital twin that currently are only manually executed by the district manager. Our digital twin is ready to do that because our infrastructure have been designed to be ready also for level 4 of maturity. So I would like to say that it is more or less easy to do this implementation. Of course, it depends on the pilot site that must have some actuator system ready and connected to the network, ready to receive message with some kind of publish-subscribe system.
So basically, in this case, we need more an hardware part that is.
Yes.
So you need actuators because once that you have a double flow of data from the real world to the digital twin and vice versa from digital twin to the real world, we need sensors for the first step. We need actuators for the second step. So it's quite simple stuff. Of course, any additional software components that are necessary can be easily developed and integrated. So basically, software and hardware are the ones that allow to go from a maturity level to another maturity level. But of course, the definition, the most complete definition of digital twin is the one in which you have a replica, as you told before, a replica of the real world object, of the real world process or asset or whatever. And this flow, this data must flow taken from sensors from the real world to the digital twin and properly processed, and simulation engine should be there with a model of the object. The model of the object can be properly trained continuously, so it can evolve a long time by keeping a certain level of compliance with the real object, and then the production of data from the digital twin to the real world must be implemented by means of proper hardware devices that can actuate the actions decided on the digital twin side. So basically, these are the main concept that we are managing in this project. Okay, I don't see any other questions in our console.
Yes, Diego, I
Yeah.
think your final comment was a good one to close this discussion. We're running a bit late.
Late, yes. But this means that we received many questions. So
yes,
good.
yes, it was a nice opportunity to exchange knowledge and get the questions from the webinar participants. And for this, I would like to thank all the speakers and the moderator for sharing the insights. And of course, thank all the participants for joining us today. We really hope you found the session valuable and gained a deeper understanding of DigiBUILD project and the digital twins and the solutions we are developing. We are always available to address to reply to questions if you need more clarifications. You can stay in touch through social media and of course visit our website. Keep an eye on your inbox as you receive the slides of the presentation today and a link for the recording of the webinar. Many thanks again, and I wish you a nice day.